pretty pessimistic out. I had two passions, a crazy experience when I was young. It's got me very passionate about poverty. Why was I so damn lucky and everybody else not? And my brother and I wanted to climb mountains all around the world. And so if we're running out of energy and industrial civilization is going to collapse, those don't go together with my two plans. So the main reason I chose to go to MIT was to work on fusion energy. Because, boy, if we're running out of the energy sources we know of, this is what powers the sun, this is enormous, and humans are ingenious, and I'm going to go work on fusion energy. I worked on solar energy in graduate school at UC Berkeley. I worked on geothermal energy for a few years after that. So I say, I don't care where energy comes from, as long as it's affordable and plentiful and lifts human lives up. That's the driver for me. But the first company I started a little less than 30 years ago was a technology company. We developed technologies for measuring the motion of fluid deep underground. So from volcanoes is magma flowing into the chamber, waste disposal injections, hydraulic fracturing. And in that company, an early on business line was the national labs maybe 20 years ago were testing CO2 sequestration, injecting it underground to get it out of the atmosphere. And so we would monitor those things. So this is a potential growth business line for my business. I'm like, I want to understand what's driving that. So maybe 20 years ago, I started to read and learn about climate change. I've probably been speaking on it for 15 years. It's a big topic. And I'm going to break all the rules of a normal talk. You shouldn't use a lot of PowerPoint slides these days. Just tell human stories. Well, I'm going to be way off the other end. You're going to see way more PowerPoint slides and graphs than you want. But I think it's important because this subject is driving decisions and changes that affect everyone's lives. And if you're going to make big decisions, they should be based on data. I usually get to extreme weather kind of the end of the talk. I talk about the physics, the chemistry, temperature, ice, all that. We'll go through that. But everyone says, well, all that doesn't really matter, with the explosion of extreme weather. When I speak in schools, that's what kids are really worried about. There's huge climate anxiety growing now among our youth. And it's a terrible phenomenon. Getting kids scared and pessimistic at a young age is not a formula for a healthy society. So I'll lead off with just 6. I just picked 6 plots on extreme weather. And the whole time scale here is 117 years. Here's what you're actually looking at. I'll come back to these. This is weather losses, floods, tornadoes, deaths from extreme weather. I don't see any large rising trends there, and you probably don't either. I'll come back to them later. But a quick thing about data sets, they're all different lengths, right? Every data set I will present, every one is the complete available data set. One of the craziest, and of course we know that in our industry, right? You want to tell a story, the biggest tool you got is change the start and end dates. And there's a lot that happens with that in climate change. I think it's critically important that we do not do that. When you have data and you want to talk about data, show the entire data set and talk about it. So these data sets have different lengths. I'll come back to them. But just so everybody can relax a little bit at lunch, no, there is not an increase in extreme weather, anything we've been able to characterize so far. Everybody knows that in this room, but the discussion about climate change, the debate about it really is about the energy system, where energy comes from. So it's important to look at sort of larger scale data. Sometimes I show this globally. This is just United States energy and where it's come. Coal on the bottom, then nuclear, liquid, little thin stripe of liquid biofuels, oil and liquids, renewables, which includes hydro, which is the dominant part of the early part of that stream. And renewables is hydro. Now it's hydro, wind, solar, geothermal, natural gas. Geothermal, tiny little thing on the top. But what you can see is when I was born, hydrocarbons were about 90% of world energy. Today they're sort of low 80s. In this EIA projections out to 2040, they've got it, somewhere in the high 70s. It's hard to change an energy system, particularly with compelling advantages for one technology over the other. As you saw, I've spent a chunk of my career and I'm passionate about energy from all sources, but they don't change fast. I notice if you look at just the oil and gas component, take out coal for a second, the EIA projections are 65% of United States energy from oil and gas in the year 2040. With the Clean Power Plan, 67% from oil and gas. With the Clean Power Plan, 65% without. So in any case, because coal shrinks and half that gets picked up with natural gas and half that gets picked up with renewables. These predictions are about the future, so we don't really know anyway. The more important data is sort of historical. There were slow evolutions of energy sources. Let's look at what's happened. This is last 50 some years, but maybe, so 6% of world energy around the time I was born came from non-carbon. So that's not just non-fossil, that's not fossil fuel or biofuels. All of human history, we were 100% renewable energy. Wood and dung and biofuels powered humanity throughout all of human history until just the last couple hundred years. Now, it still took many decades to transition, but that transition over meant that between hydrocarbons and traditional biofuels, 94% of energy when I was born. Then we had the arrival of nuclear power and large-scale hydro. They took not a giant, but a meaningful chunk of world energy. And 25 years ago, 13% of world energy came from non-carbon sources. And that screamed up to almost 15%. So less than 2% move over the last 25 years. So people think things are turning upside down, the energy system's changing. That's not actually what's happening. Another comment, I said carbon sources. I personally can't stand that term. It's like calling salt chlorine, a toxic gas. Human life is based on carbon. All biology is carbon and carbon chemistry. So of course it comes in many different forms, but calling CO2 carbon, we're sort of stuck with that abbreviation, but not a good one. All right, the next two slides are my summary. You want to nap for the rest of lunch, get the next two slides, and you've got the key thing. First, the facts. Is the climate changing? Yes, it always has. It is a nonlinear, dynamic, chaotic system. It is always changing. Has the Earth warmed over the last 160 years? And the reason I say 160 years is that's the length that we have a reasonable modern temperature record. Modern meaning reasonable quality instruments spread over some coverage over the globe. Has the Earth warmed? Absolutely. By about a little less than 1 degree centigrade. All climate, and of course science in this field is all done in metric units, so I apologize for that, but 0.9 degrees C is 1.5 degrees Fahrenheit. Probably everyone in this room knows that. That's over the last 160 years. So it's meaningful, it's real. I think humans are playing a meaningful role. But to put that in context, if we change the temperature during my talk by the warming we've had in the last 160 years, the majority of the people, certainly including myself, would not notice that temperature change. It's the equivalent in Houston of moving 50 miles north. That gives you a 0.9 degree change in average temperature across the United States. It's sort of our rough temperature gradient in a season. Does increased CO2 in the atmosphere contribute to global warming? Absolutely. CO2 absorbs long-wave infrared radiation. I'm going to talk a little bit about that, probably a little more than you want to hear about that. And that leads to warming, contributes to warming. Has our burning of hydrocarbons been the main driver of increasing CO2 concentrations in the atmosphere? Absolutely. Pre-industrial times, we don't know exactly, but it seems about 280 parts per million. In other words, 0.03% of the atmosphere was CO2. Now it's 0.04%, or 415 parts per million. So about a 50% rise over the last 80, 100 years. Most of that really over the last 75 years. When we double CO2 concentration in the atmosphere, I think it's highly likely we will, if you project the current rates of increase in CO2, probably around the end of this century, we'll double the CO2 concentration in the atmosphere. How much would we expect the planet to warm from that doubling of CO2 in the atmosphere? About 1.3 degrees C, 2/3 of which has already happened, in the absence of feedbacks. All of these statements are not controversial. This is just simple radiation physics. We're already in pretty deep in saturation on CO2, but if you increase it by a factor of 2, how much more does that check? The Earth's ability to lose infrared radiation, its only way to cool itself, it's about 1.3 degrees. The question is, is there feedback? So the technical question always is, that's without feedbacks, but feedbacks could multiply that, could cause the warming to be 2, 3, or 4 times that large, or negative feedbacks could suppress it. But all of the statements on that thing, I think, are relatively uncontroversial. There are controversial things. And so now I just come to, this is just sort of basic logic in my mind, and I hope this is also, well, at least among logical people, probably not that controversial. Is aggressive action on climate change warranted? To me, if global warming is significantly amplified by positive feedback, and the postulated mechanism of this is water vapor. When it gets warmer, more water evaporates. Water vapor is a way more important greenhouse gas than CO2. So if we lead to not just more CO2, but more water vapor, maybe this warming will be significant. It is also relatively uncontroversial that 1.3 degrees C of warming by the end of the century, 0.9 that's already happened, is a net positive for humanity. The Intergovernmental Panel on Climate Change does these economic studies. I'll talk about those later. But it is uncontroversial that 1.3 degrees C of warming leads to more positive benefits than negative. Nobody would think that's a big deal. So you have to have meaningful positive feedback for this issue to be potentially a negative for humans. You also need that the amplified net warming results in significant net negative impacts. Very possibly that's true. We need to take aggressive action. We have to have policies that'll significantly reduce CO2 emissions. Those policies would have to be implemented by all, not everybody, but all the major nations. So that there's only one atmosphere, so CO2 is a well-mixed gas. So you've got to get all the major players to do the same thing to be able to change CO2. And then the last, or when I say CO2, think greenhouse gas equivalent, nitrous oxide, methane, there's other greenhouse gases, but CO2 is the dominant one. And then the fifth thing that I think needs to be true logically is that the cost benefit of these policies to combat climate change or reduce greenhouse gas emissions have to have at least in the neighborhood or comparable returns to other major issues the world faces today. Indoor air pollution, I talk about this a lot. This is people still cooking and heating their huts the way all of our ancestors did, burning wood and dung inside. A third of humanity still does that. That indoor air pollution kills 3 million people a year. Outdoor particulate matter, which mostly comes from deforestation, burning wood and solid fuels outdoor. It comes from coal without scrubbers and bag houses. It comes from poor, dirty industries. Outdoor particulate matter kills 4 million people a year. United States, of all the major economies, has the cleanest, lowest particulate matter in our air, below the WHO threshold for meaningful health impacts. But poor countries don't. So 4 million people die from that. Lack of access to clean water, these are all World Health Organization data, kills about 5 million people a year. Malaria still kills over 1 million people a year. Poverty, hunger, malnutrition kills about 7.5 million people every year. So are there challenges on the planet? 100%. There's lots of them. Climate change is even one of them. But to invest massive resources in urgent action, it has to be a real problem that we can address, and that using those resources in this direction is never have to be comparable, but at least in the same order of magnitude of putting those resources somewhere else. All right, let's get into the detailed technical stuff. So the whole idea of climate change, global warming, is that when you combust the simplest hydrocarbon, methane, simply oxidize it. You take one methane molecule, you combine it with 2 oxygen molecules, there's 2 products of that. A CO2 molecule and 2 water vapor molecules. You see all those scary pictures of those big clouds rising up, they're global warming, that's water vapor. When I was young, those clouds were brown, were black. They had pollutant and particulate and stuff in them. Today, they're done, when they're white clouds, they're water vapor. CO2 is odorless and transparent. But this reaction liberates a ton of energy, but it increases CO2 in the atmosphere. So the nerdiest slide of all is simply the thermodynamics or the heat balance of the Earth. So there's 3 ways you can transfer heat. There's one we learned when we're young and you're kids, and you put your hand onto a hot stove, that the hot body heat flows down a gradient, flows from the hot stove into your hand, and it hurts. but that's conduction. These molecules are vibrating faster than those molecules, and they cause the molecules in your hand to vibrate faster. That's what heat is, just the average vibration velocity of the molecules that make up a body. I stuck my tongue on the chairlift in a very cold day to feel how cold it was when I was a kid. There, the heat was flowing out of my tongue into the chairlift, and my tongue froze onto the chair. And my dad was convinced I was never gonna make it in this world today. And I think pretty good reason to believe that. So that's conduction of heat. The other one, super common and probably the biggest from an atmospheric or weather thing, is convection. Convection is, it's cold in Denver, but a new air mass from the south blows in and it rapidly warms up. That's not the sun absorbing heat. That's not conduction, that's convection. A new body of a different temperature moves and convects heat. Cold air masses coming from the north, that's different air masses with different heat content moving and carrying heat with them. That's convection. The third, so the earth, right, gets warmth from the sun. And then how does it cool off? You gotta, to have a constant temperature, you gotta balance heat gains with heat losses, right? Space is empty. So there's no convection of air out over to that colder Mars. There's no conduction because there's no molecules in space to receive that heat. So the only way the Earth loses heat is they call black body radiation. When something is a certain temperature, it emits radiation that's proportionate. It depends on the temperature, the length and intensity of that radiation. That's how those awesome night vision goggles work. Human body's a certain temperature. We're emitting black body radiation, and at night, we're meaningfully warmer than the area around. And so we're emitting not visible light, but longer wavelength infrared radiation. That's how those glasses work. So the Earth does the same thing. First of all, the sun has black body radiation too, right? So the wavelength, another way of thinking of the energy of each photon or each packet of light that comes, depends on the temperature. The sun is very hot. It's not the center of the sun that matters. Where does the light come to us? It's emitted from the surface of the sun. So the surface of the sun is around 10,000 degrees. 10,000 degrees equates to a certain wavelength of light that gets emitted. And as you can see in this little lump on the left, the dominant energy that comes to us from the sun is in the visible wavelength, right? That's probably why our eyes evolved to see, in that wavelength range, because that's the dominant energy the sun is emitting. So the Earth is dramatically cooler, and of course the relative temperature of the Earth is the top of the atmosphere of the Earth radiating away. So we're much cooler, so we radiate at a much lower wavelength. That's infrared. So the right side there is what is the radiation that actually escapes Earth? How do we lose heat? The bottom line is wavelength of light. And you can see it's not that smooth bell curve, Boltzmann curve you'd expect from black body radiation. It's truncated on both ends, and that's because those pieces of the radiation are absorbed. So the first line is the total amount of radiation that's absorbed. Going down, you can see water vapor. Dark means it's preventing at that wavelength either all or a large amount of that. Water vapor is the dominant absorber of infrared radiation going out. On the cooler temperature, longer wavelength end, CO2 has a bandwidth range at which it absorbs as well. Methane's got a different one, as does nitrous oxide. So it's these gases and their concentration that doesn't let all that radiation naturally leave the Earth. Part of it gets absorbed, re-radiated, and some of that comes back down and stays in our atmosphere. Thank God we have water vapor and greenhouse gases, because with the energy we receive from the sun and the black body radiation of an Earth without any atmosphere, our average temperature would be right around or just below freezing, average across the globe. So it'd be very cold, we wouldn't have a lot of liquid water, and life wouldn't be possible. But thankfully, we got a lot of water vapor, and we have a climate that we've evolved to live in. Big picture of climate history. And look, everybody, most people don't know this stuff. People in this energy industry know this. 100 million years ago, 200 million years ago, the Earth was dramatically warmer. A warmer world means a wetter world and more abundant life. So think of the dinosaurs or Jurassic Park. Where I live in Denver, that's dry and dusty once you get outside the city. This is what Denver looked like when the DJ Basin oil was sat down. Just massively warmer, massively more CO2 in the atmosphere, a lot of life laid down. Thankfully, that's so. It's during those times, of course, that stored solar energy, otherwise known as oil and gas, was laid down in copious quantities and is employing us and powered our world. But the Earth has been in very different states as well. We know there's at least twice where the planet froze entirely, surface of the planet, meaning the oceans at the equator were frozen for millions of years. At least twice, arguably 3 times, this has happened. So another funky chemistry thing. Thank God water is a unique molecule. Most things, they have a large volume as a gas. The volume shrinks when they go to liquid, and it shrinks again when they go to solid. Water doesn't shrink when it goes from liquid to solid. It actually expands. So our ice cubes float. If that wasn't true, the oceans would have frozen from the bottom of the ocean all the way up, and we wouldn't be here. So thank God for that quirk of water, that it froze at the surface, and that growing ice at the surface of the ocean provided insulation, and the water below, tens of meters of frozen ice, was still liquid water. Because to have life, the life that we know of on the planet, you need 3 things. You need a carbon source, that's dominantly CO2 for the world today. You need liquid water, and you need oxygen. And liquid water was put at grave risk, but it survived. This is geologic proxy, so this is 500 million years. And blue is temperature. You can see we didn't have any very accurate thermometers sitting around 500 million years ago. So these are proxies for this, and black is CO2 concentration. From geologic record, we can get a little bit better estimate of what was the atmospheric CO2 concentration throughout history. And then on the far right is the current day. And so in the very big picture, you can see we live in a remarkably cold, CO2-starved time in the history of life on Earth. Now, humans evolved in that time, so it's not alarming for us, but in the history of the planet, if you look way back as well, you'll see times where there was massive cooling of the planet when CO2 levels were high and rising. There was massive warming of the planet when CO2 levels were falling, and vice versa. So CO2 is a greenhouse gas. It should play a role, but has it been the dominant knob that's adjusted the climate in the world? Well, the geologic record would say absolutely not. So 500 million years, let's zoom in to more recent times, relevant on a human scale. This is an ice core. This is 450,000 years of data. Blue is temperature, red is CO2 concentration, and the present is over there on the right. So the way to look at this, you look at, wow, we live it's dramatically warmer now than it was 20, 30,000 years ago, right? We technically live in an ice age. Humans have evolved the world's been in an ice age for about 2.5 million years. But in this ice age, we have long, relatively cold. My house in Montana was under a mile of ice 20,000 years ago, and likely will be again 20,000 years from now. I probably won't be in it, so that's okay with me. And then we have these warm interglacial periods. The one before us was called the Mania warming, and you can see them going back. The warming that humans, society, meaning agriculture and written language and all that evolved, had been in a little bit cooler interglacial period than the previous ones, but still conditions obviously great for humans to thrive. The other one is the CO2 concentration versus time there. Al Gore used this completely disingenuously. I don't believe he didn't understand this fact. In Inconvenient Truth, you see that great correlation between temperature and CO2, and he got on his cherry picker to lift it up because CO2 is going up so much, so we're gonna have 10 degrees C or more of warming. But they're different phenomena. These interglacial periods are driven by, we believe, and I think there's more confirmation coming, Serbian mathematician 100 years ago, Milankovitch, that noticed the angle at which the Earth is set from straight up, with this 23-degree angle, that angle moves with time. How round the Earth orbit is, eccentricity changes with time. The angle of the Earth also has a precession around it. So there's 3 different cycles over different time scales that seem to be the cause of these cooling and warmings. And without going into too much detail, it's basically when a lot of sun hits the northern hemisphere, because that's where most of the land is, you have warmer times. When the sun is more skewed to hitting the southern hemisphere, where it's mostly ocean, and the northern hemisphere that can build ice masses on land gets less sun, you get glaciers, and you get the positive feedback of more glaciers, that don't absorb the sun as well, and you get these very cold periods. But in the last one, you can see when the temperature warmed up, of order 1,000 years later, the CO2 started to increase in our atmosphere. So temperature is the driver, CO2 is the follower. And the reason is when you take a really cold beer out, you pop it open, there's not many bubbles, or your soda you don't spill on yourself. If it's hot and you open it up, poof. When liquids are warm, they can't dissolve as much gas. They can't dissolve as much CO2. When they're cold, they can dissolve a lot. So it doesn't come out as easily. So as the planet warmed, the oceans got warmer, they released dissolved CO2, and that's why atmosphere grows. But temperature drove CO2 fall 1,000 years later. We're at a very different time now. Now we are increasing the CO2, so it's sort of a different experiment. We're increasing the CO2 atmosphere, and the question is how much is that warming going to cost? All right, let's get to measured data. That's proxy data. Fortunately, in the center of England, we have the oldest continuously recording thermometer since 1659, so over 350 years of data. And all I've done here is averaged the temperature in December. I could have done any other month, but averaged the average temperature in the month of December for that particular year. So there's just one data point for each year. And the point of this plot is, if you look carefully at it, you can see it has warmed 1.5 to 2 degrees C over the last 350 years. The Earth was relatively cold 350 years ago, the so-called Little Ice Age, which followed the medieval warm period where the Vikings lived and farmed in Greenland. This was a cold time. We've gone to a warmer time. So there's a modest warming there, but what you can see is the year-to-year variation of temperature is just dramatically bigger than even a multi-100-year trend. So people say, oh, God, it never got this hot when I was a kid. It used to always, that's a little bit of confirmation bias, right? There are real changes, but they're relatively subtle, the year-to-year variations. And somewhat humorously here, the December in 2010 in England was the coldest December in the 350-year record. Doesn't mean England's getting colder. It just meant that year had a large temperature departure to the cold. This is degree C temperature scale, average across the globe from 0 degrees to 30. So if we just put the annual temperature variation in Houston, it would go off the top of that plot, it would go off the bottom of that plot, but averaged over across the whole planet, you can see we're kind of around 13.5 degrees C average across the planet. On that time scale, it's not very interesting to look at. This time scale, it's more interesting to look at. And average the data. So look at the red line, for example. The red line is a trailing 5-year running average of temperature. Because there's El Niños and La Niñas, there's all sorts of things. There's volcanoes, there's all sorts of things that change the temperature. If you smooth it out and average it over a long term, this is the surface temperature record. So this is this 150 years I was talking about. You can see from 1910 to 1940, we had a relatively rapid warming period. Then we had a plateau and sort of a gradual cooling period. The end of that time period was the great global cooling scare, even though it was, globally quite modest cooling. Of course, you could find geographies where the cooling was quite significant. And then we had the more recent, quite large warming from the late 70s that ended the global cooling scale up to about the year 2000. There was a big El Nino in 1998. You had 15 years of relatively flattish temperature. And then we had another meaningful El Nino in 2016, which doesn't show up in this data and led to some warming of the Earth. That's sort of a progress of the warming we've seen. The best data we have by far, it's not manipulated, it's not site selection issues, it's the least questionable satellite. There's these radio sondes all over the planet in orbit, and they measure just from microwave radiation sondes. They measure the temperature of the atmosphere at different altitudes and different depths and provide a continuous temperature record. This is the gold standard of temperature monitoring record. So in the red, it's sort of an average of all the global climate model sort of predictions of temperatures. The blue are the satellite data sets. We also send balloons up and measure temperature at different heights, so it's another way to measure temperature. They're in green. And this is a very generous look at the predicted models. So you can see the variation of predicted models went up in 79, they went down, they went up again. This is Mount Pinatubo, called the Large Global Cooling. The models don't predict those things at all, but they hindcast by adjusting a fudge factor. We'll put more aerosol in the atmosphere and reflect heat back out. They can hindcast and fit things, but they don't forward cast and predict things. Forward casting is a more simpler prediction. But if you bring it all the way down and say the bottom of Pinatubo, okay, that's baseline. Then in that case, the models so far have predicted maybe a little more than twice the warming rate we've actually observed. But that's maybe an overly generous way to look at models. Another way to look at them is to say, keep their underlying warming trend, a Pinatubo thing only relative to the scale of Pinatubo, but not reset the trend at 1998. And then, if you look at it this way, you can say, okay, they're over predicting the warming by a factor of 3. But thinking roundly those numbers, we should always probably err on the generous side to say the models to date have predicted warming at sort of twice the rate that the actual measured data has shown. So why are the temperature models so wrong? My guess is most likely uncertainty around clouds. And real quick, without getting too technical here. As I said, in simple radiation physics, the end of this century, we should have 1.3 degrees of warming. We've had 0.9, and that's right, it's a logarithmic function. Going from 280 to 415, which we've done already, much more warming in that than adding the same increase in CO2 going forward. This is logarithmic. Every new CO2 molecule causes less warming than the last. So we should have had about 70% of the warming so far, and we have about. So to have an issue, you've got to have positive feedback. So these climate models, they're giant finite element models with all sorts of cool chemistry and physics in them, but the blocks are tens of miles on the side that they spread the Earth into. Clouds are micro nucleation points formations. Clouds themselves aren't tens of miles inside. So they don't model clouds at all. They just have a factor. Again, sort of a little bit of a knob, a fudge factor. How much increase in water vapor is there? How much stays resident in the atmosphere? That's the only way you get positive feedback. You want to have a story, you want to have an issue, you got to have 2, 3, or 4 times positive feedback. So they don't claim that they model or represent clouds. They just say that a warmer world should evaporate more water vapor. If some of it stays in the atmosphere, that should lead to more warming. And, hey, here's our guess of that positive feedback. To date, I don't think the models line up too well. So maybe they're not doing clouds very well. The data, the actual current warming rate, I think I'll show it in a second, is actually right at 0.13 degrees C per decade. Kind of along the lines of what you'd expect with no positive feedback. Models assume this large positive feedback. Perhaps, there should be an increase in evaporation of water vapor. Perhaps it nucleates, it condenses in clouds, and it rains. The measurements of water vapor around the atmosphere as well, we haven't been able to detect any increase in water vapor. This is sort of a big unknown question. There are also, because of the greenhouse effect, there should be a particularly warm spot in the tropics and in sort of the mid-troposphere. That warm spot does not appear in the radiation thing or in the measurements of atmospheric temperature profiled over. So the real story is it's a very complicated problem. It should lead to warming. How much, we don't know. How does that evolve? What are the feedback effects, both atmospherically, the ocean circulation currents? There's so many things that impact climate. It's complicated. But we are warming. We are increasing greenhouse gases. So the IPCC has also, their first assessment report came out in like 1990. And about every 5 years, they put out another one. The 5th assessment report came out 5 years ago. The 6th assessment report will come out. So yellow, and it's mostly covered up. In 1990, they projected what should be the trajectory of atmospheric methane based on their models and based on this warming. So the bottom of the yellow, it's kind of coincident with the bottom of the other ones there. And then the top of the yellow is super high. So that's their 5 to 95% confidence bounds. Global atmospheric methane, once you got a year or two into it, was not in their 5 to 95% confidence bounds. So they reprojected in the second assessment report in 1995 as well, 5 to 95% confidence bounds. Third assessment report, fourth assessment reports. And to date, methane has not broached into their 5 to 95% confidence intervals. So I think it's probably reasonable to say they've overestimated the rise of atmospheric methane as well as they have with temperature. Oil and gas industry is like 18% or something of the source of atmospheric methane. Wetlands, agriculture, landfills are large sources of atmospheric methane. Here's the one maybe shocks the kids the most. Global sea ice, right? So this is a cool topic. You see a lot of stuff on sea ice, but for some reason the media, they only talk about the Arctic ice. But as far as I know, a sphere and a globe, we got a North Pole and a South Pole. So if you take both of those, how much ice is floating on the ocean of the two poles, and sum them together, and this data is online a few clicks away. There's awesome data sources for all of the stuff I'm talking about. None of it is my data. It's all downloaded from other sources. But if you look at global sea ice, since the start of this satellite record, we've got pretty high quality data, 1979, you can tilt your head, but I'm not seeing a giant trend. In fact, until a few years ago, no trend at all. But something did happen. So here's blue is Arctic sea ice. Arctic sea ice has been declining for the last 40 years, and Antarctic sea ice has been growing, and they've been at roughly similar rates. There was a huge storm, sort of a giant wind event down in Antarctica that blew a giant amount of ice out of the warmer waters that have melted. And as you can see right there was a meaningful shrinkage of Antarctic sea ice a few years ago. That has not rebounded yet. So if I show here, that was my only exception, if I show here the updated to today data set, you can see no trend at all in global sea ice. You can see a little step change down where we lost maybe 8% of global sea ice, and it's been sort of flattish at that new level. We've not rebuilt that level of Arctic sea ice down there. But at the Arctic, there's no doubt, most of the warming that we've observed so far is in the North Pole. South Pole doesn't seem like it's warmed at all. Most of the warming has been at the North Pole or the northern latitudes and at night. I have another plot I'm not going to show that shows the warming, the difference in temperature now versus 100 years ago versus latitude. Southern hemisphere, almost nothing has happened. At the equator, almost nothing has happened. But the further north you go, the larger the warming has been, dominantly at night. So we are indeed seeing meaningfully warmer nights in cold places. That's the biggest chunk of the warming. So I live in Colorado, and like where all of you guys live, they endlessly have news stories. The ski areas are all part of a climate coalition to save their snow, and our industry, Colorado's tourism, is like our only industry bigger than oil and gas, and it's under threat for climate change. And so they pick interesting start years, and they show these decline in Colorado snowpack. But again, I think a key for us is never do that. Take the entire data. So Colorado, we have about 82 years of snowpack data, and there's our 82 years of snowpack data. And if you fit it, I mean, it is dead flat line. And you can see the last few years have been big snow years. So they don't show those plots anymore because that ability to draw that, they still say those words, but they don't show the plots anymore. But look at the data. You know, every kid I talk to in the school thinks snow's going away in Colorado. I mean, I don't know the future, but for 82 years, it's been roughly flat. Looking back in that like early 80s and late 70s, you can see two really bad years. My dad bought a condominium. We were all skiers, all four of us. I'm the youngest of four kids. My senior year in high school, so just when his kids are about to leave, he bought a ski condominium. And it was in that horrific year, that really short year. Breckenridge, where they bought the condominium, was open for 5 days that year. Open February 4th, closed February 8th, the entire year. So weather is wildly variable, and that was true 100 years ago, and that will be true 100 years from now. And woe is me. Snow cover, so that's Colorado, because I care about Colorado. Here's the northern hemisphere. Again, not a huge amount of land in the southern hemisphere. So think Siberia, northern Canada, Alaska, and then in the wintertime, snow comes down and covers further. So this is sort of permanent snow cover from satellite imaging. There's also, 72 or whatever. Here's roughly 50 years of data, and here's a shocker. It's bigger in the wintertime, it melts off in the summertime, goes back up in the northern time. But that's northern hemisphere snow cover, continuous complete data record. Anybody see the rapid disappearance of the snow in the northern hemisphere? I think it's roughly offsetting factors. It's gotten slightly warmer, which does make it easier to melt snow. But when you get slightly warmer, it means slightly wetter. So there's slightly more snowfall. And of course, the areas that are right on that threshold where they could withstand snow and they can't withstand snow, that's a relatively narrow band. So no change. Like in Colorado, what we see is you hear a lot about, there's actually, if you just look in the spring months, there's less snow in the Colorado mountains in the spring months. That's true. There's more snow in the Colorado mountains in the fall, and the winter's about the same. But if you just talk about spring and you do selective years, you can tell all sorts of stories. So it's very important, and again, for us or for anyone, I think in scientific data, is always present the full data set. I know we do type curves and well costs and all that. We always present the full damn data set. I know we do. Sea level rise. Look at the bottom plot as a temperature proxy at the top, but look at the bottom. That is global sea level rise over the last 300 and some years. It's from tide gauge data. So, and boy, there was, like San Francisco, they had a town hall meeting in my little town of Mill Valley that what we're gonna do about climate change. In San Francisco, sea level is actually slightly falling. And it's falling because there's a rebound in the plates. Sea level is not the same everywhere. It's wildly different. There are places where sea's rising quickly just because of plate motion. There's places where sea level is falling. When you draw groundwater out, you can also make sea level rise independent of anything going on with the oceans. But so when you look at sea level, you want to look at the globe, unless you're looking for a specific region. But it's risen at round numbers, 10 inches a century, or 1 inch per decade, for about 170 years. And if we go back again 15,000 years ago, it's risen 400 feet. A different thing. That was the end of that glaciation. A huge amount of water left the land and went into it. It was flattish during the Little Ice Age when temperatures weren't changing a lot, but it's been rising a long time, certainly well before humans meaningfully changed CO2 concentration in the atmosphere. But we are doing that. That is leading to warming. That will add to sea level. So all those things are real, but look at the data. So there's a different way to measure sea level now, which is from satellites. So this is like satellite interferometry over all the oceans of the Earth. This is done at CU Boulder. And if you look at that record, it's 25 years, something like that, 26, 27 years. Anybody see a huge increase in the slope or the rate of rise? It shows about a little more than a foot a century. It actually shows a higher number than the tide gauge data. But if I plotted the tide gauge data during the same time frame, it shows a lower rate. So they're fundamentally measuring different things. They both see a relatively constant rate of rise. The satellite shows a little bit higher level, but in neither case do we see a rate of increase of the rise. So when they talk about 3 or 10 feet of sea level rise next century, I don't know what data they're extrapolating, but it's not in the historical data. Here's one particular location. This is tide gauge in New York City. So James Hansen, who was the climate scientist at the NASA Goddard Institute of Space Sciences in Manhattan. He's the guy who really started the climate change movement in the United States, testified in Congress in 1988. That's when they found the hottest day and they opened the windows, they turned the air conditioning off. It was great theater. And Jim Hansen said, my office at the NASA Goddard Space Institute will be underwater, likely underwater in 40 years. His office on the west side, you gotta get over the West Side Highway, probably takes about 10 feet of sea level rise to do that. He said in 40 years, that was 29 years ago, so we're 70% the way through, and it's continued at that same rate. It's been rising about an inch a decade. So he's got 3 inches out of his 10 feet, but still got 11 years left. Maybe there's 9 feet and 9 inches coming, but the data doesn't seem to support that. Extreme weather data, I showed a quick summary of that. By far and away, the most important thing in extreme weather, right, is what does it mean to human beings? What does it mean to people's lives? So I debated climate change on TV a couple of times. I debated a gal who was a climate change activist. And she said, but you got to admit, 30,000 people a year are dying from climate change, over the last decade, or dying from extreme weather. And I'm like, it's absolutely right, and it's absolutely tragic, but 100 years ago, that was 450,000 people a year that died from extreme weather. And the population has quadrupled since then. Your chance of dying from extreme weather, meaning all the citizens of the world, has shrunk 98% over the last century and still dropping. It isn't that extreme weather ended and hurricanes stopped and floods and all that stuff stopped. It's just a wealthier, more energy endowed society is better able to deal with these things. And it's really a tremendous story of human progress. The last 200 years, my view, the primary catalyst, the growth in human liberty, bottom-up organization, not top-down organization, and the massive explosion in energy available to every human has doubled human life expectancy, caused poverty to plummet, has allowed us to save forests now instead of using them for fuel. I think it's been enormous. And of course, it's saved countless lives just in saving people from deaths from extreme weather. Last year, I think is going to be the record to date ever recorded in this database. 11,000 people last year died from extreme weather. And where are those 11,000 people? In poor countries that are not energy rich. So this problem's not gone, but it's shrinking dramatically in places that have energy. And the reason this curve looks so smooth, it looks like bullshit data, it's because it's averaged over 10 years. 10-year running average from the world. This is a government database. But average it over 10 years and you get a curve that's a little better to look at. Global weather losses as a percent of global GDP. People say that we have more billion-dollar storms than ever. Well, we have inflation, we have increased wealth, we got more houses on Florida, so that higher gross dollars of storm damage, of course, that means society's getting wealthier. Not only if you get twice as wealthy, you have twice as much, but when people are twice as wealthy, they've got 5 times as many beach houses, more people. So if you look at it as a percent of global GDP, that's the trend again. We only have this data set from 1990. That's the entire data set. Doesn't look to be going up. Tropical cyclone landfalls. This is across the planet. Again, we've got pretty good data for 50 some years. You might see a big upward trend there. Hurricane data, this is US hurricanes on the left, all hurricanes on the right. It's major hurricanes landing in the US. I'm not seeing a trend there. Here's the really nerdy one. This is total cyclonic energy. All the cyclones integrated over how much energy they're dissipating through time. Maybe some IR guys can show an upward trend out of that data, but I'm not an IR guy. Tornadoes, violent tornadoes. So this is F3 and above. The tornadoes we worry about, the tornadoes that kill people and scare us. This one's lucky. It's actually on a meaningful downward trend. Don't know why, let's call it luck. Flood damage as a proportion of GDP. This is United States. This is from 1940, downward trend. Again, this is wealth. This is investment in infrastructure. This is dealing with things. Doesn't mean rainfalls are different. The raw extreme weather seems to show no trend. Human reactions to it seem to cause downward trends in things we care about. There's drought, 100 years of drought data in the United States, extreme and less extreme. North America is the blue. You can see the 30s were by far and away our worst drought times, but no long-term trend in droughts. Here's the same data for the globe, different levels of drought, severe, not as severe, and all that. But as you can see, none of this stuff, weather moves around, climate systems are complicated, but no increase. The Intergovernmental Panel on Climate Change put these in their reports, that there was concerns and threats, and it was great PR, but it's a scientific body. In the last version of their report, these are all still in there, low confidence, low confidence, low confidence. They've essentially taken out any claims about extreme weather, but that hasn't filtered through to politicians and media. I mean, it's a great story, it's great press, but it's not true. Glaciers, I'm a mountain climber, so this one's personal to me. Global glaciers in the world have been retreating for, again, about 200 years. The slowdown, the start of the end of the Little Ice Age. So that's been going on since long before fossil fuels were even meaningful. But is it going on today? 100%. Even in the tropical, I climbed in Ecuador a number of times. In fact, I was married in Ecuador. Temperature hasn't changed at the equator. In the Andes, temperature hasn't changed. Glaciers are shrinking massively. I think this is, I bet, 2 factors. One, deforestation to grow crops means less moisture in the air, less snow falls in the cold periods. And when you clear soil, you create much more dust. That blows onto glaciers. When you put color or anything that's not white, you melt a lot faster. Maybe why the North Pole is losing sea ice and the South Pole isn't. I don't know. What to do? consensus plan, reduce CO2 emissions at all costs. Burning less fossil fuels is the only way to do that. You can either reduce energy consumption for everyone, or you can replace it with other energy sources. The problem to date is alternatives are much more expensive. Again, also contrary to what you hear, this is what the data says. The Kyoto Treaty, I made this slide like 15 years ago when I first gave this talk. And the Kyoto Treaty, if everyone had met their commitments to the Kyoto Treaty, it would have led to the Earth being 2/100ths of a degree cooler. We led to the ethanol and rush to biofuels, led to a surge in grain prices, and Indian economists estimated that killed 200,000 people a year. When you increase the cost of energy and you increase the cost of food, you massively impact people's lives. So was the damage, and of course, like only two nations, the US and Germany, because the collapse of East Germany really met their Kyoto targets. We didn't even ratify the treaty, we did sign it. But you gotta look, to me, everything's about cost benefit. Everyone had done everything in that. What's the world benefit of 2/100ths of a degree less warming? Here's emission trends. India's on the bottom, and all the developing countries are on that trend that India's on blue. They're just rising up. I cheer that rising. That means people are living longer. They're getting better lives. They're going from burning wood and dung to burning liquid petroleum gas. They're riding on a motorcycle instead of walking, or they're getting on a bus. Their lives are getting better. I think it's actually a huge plus to the environment too. Poverty is the greatest threat to the environment. China's the giant rise there. China plateaued for a few years. China's back rising again. This is I think it'll rise meaningfully next year as well. But again, it's people rising out of poverty. Sometimes systems can change fast. Here's two cool pictures, only 13 years apart in New York City. The one on the left is all horse-drawn carriages and one car. The one on the right is all cars and one horse. 13 years. This is just one city. Global transportation didn't change in 13 years. But if you have something that makes people's lives better, it's cheaper, cleaner, and enhances their lives, people will adopt that fast. Market-driven things can happen relatively quickly. Top-down things rarely do. So the Paris Agreement, zero binding agreements to do anything, $2 trillion in subsidies globally over the last 20 years, dominantly for wind and solar. They're the politically powerful thing. I worked on solar energy. I'm not against it. But what did that get? Less than 2% of world energy last year. Less than 2% came from wind and solar. That, to me, is a little premature to call that an energy transition. Rich country electricity grids, is that happening? Yes. What does that mean? It creates enormous vested interests. Electricity prices have risen. I'm going to show that in a second. And of course, when electricity and energy prices rise, that has a negative impact on human lives, particularly low-income people. Low-income people are not politically powerful, so when you squash them, that doesn't stop a policy. When you start to hurt other people, you get pushback. Here's a simple plot of installed renewable capacity per person versus retail electricity price in that country. It's a 0.84 R squared. Increased renewable capacity, more expensive electricity. United Kingdom did a public health thing. They estimate they kill about 25,000 people a year from their higher electricity prices. These are low income, mostly elderly people that can't afford to heat and cool their houses to save temperatures. Germany's electricity prices have risen massively more than the United Kingdom's. So, and what was the success in Germany in their energy transition? Two quick facts. They reduced as a percent their greenhouse gas emissions massively less than the United States over the last decade. And they get 86% today, 86% of the total energy in Germany is from fossil fuels. 81% in the US, about 82% for the globe. They still get a larger percent of their total energy from fossil fuels. After in Germany, the total investment, $400 billion. They did get a doubling of their electricity prices, so they're now triple the United States is. They are hurting blue-collar jobs, they are harming poor people, but changing an energy system, reducing greenhouse gas emissions, incredibly hard problem. This is Bloomberg New Energy Finance data on clean, and I say clean in quotes. There's no such thing as clean energy and dirty energy and renewable energy and non-renewable. These are marketing terms. Every wind turbine has 100 tons of coal in it. in the steel. You gotta take the iron to make steel, you gotta put coal inside the turbine. Hundreds of tons more of coal to get that carbon into the steel. The blades are made out of oil and gas. They're mined with oil and gas, they're transported, they're maintained, they're installed. So they're not zero carbon sources. They are lower total CO2 greenhouse gas emissions, maybe 2/3 or 3/4 lower, but calling them zero, and of course the life of a wind turbine is 20 years, about the same as an oil well, except it needs much more steel or whatever. So renewable, clean, not clean, these are marketing names. They are different, and they do have different profiles. But in any case, the rise in energy costs in countries that have invested hugely have led to about a 10% drop globally in clean energy investments, clean in quotes, in 2018 over 2017. And this year, it will be down more than 20% globally. Economics. So here's maybe single most important slide. I talked about the science. And again, when I'm talking about the science, I'm showing here's the Intergovernmental Panel on Climate Change projections. Here's the actual data. I think they're overstating things. I think the science supports their overstating things. They themselves have lowered their rate of warming targets. They have dialed down a little bit of the rhetoric because the empirical, or a little bit of the science because the empirical data has shown so. But that's a small disagreement compared to what the IPCC says in studies compared to what you hear in the media and politicians and all that. So the Intergovernmental Panel on Climate Change, the bureaucracy set up for this cause, does economic analysis of climate change, as does, in somewhat in cooperation, William Nordhaus. So the first guy to win a Nobel Prize in climate economics. He's a Yale economist. He's awesome. 2017 Economics Nobel Prize winner. So they're studying what is the impacts to the planet, to humans of the planet, to the economy of the planet, if we don't do anything. We let business as usual go ahead. There's no investments in clean energy, no climate mitigation. And they've come to similar conclusions. 2.5 degrees C of warming. Remember, we've had 0.9. We're warming at 0.13 degrees in a decade over the last 40 years. So that means it's over a century more. We're somewhere in the middle of the next century or early in the next century at the current trends that we get to 2.5 degrees C warming. They estimate that would be doing nothing leads to a 2% reduction in global GDP. 2%. They also estimate in these models that the world then, the economy, is somewhere between 300 and 500% larger than it is today. So 2% sort of less than a year of growth over a century. So the IPCC does not claim this is a crisis. That is not their data, that's not their economics. That is the politicians, that is the media. And 4 degrees C of warming, which again, you either have to have massive positive feedback or you got to go out more than another century, 5% reduction. Of course, are those numbers accurate? No, who knows? But that's the people promoting it. The IPCC, to be honest, actually had a range between 0.2% and 2%. I've taken the high end of their range for 2.5 degrees C warming. So in any case, you hear a lot of stuff, but the data, the scientific data, the economists in the IPCC certainly see no emergency at all. And the other thing, and I'll show this quickly, that this economic analysis of climate change shows that the negatives only exceed the benefits, somewhere between 1.5 or 2 degrees C warming. So maybe 50, 70 years from now, climate change should become a net negative. Today, in the simple economic modeling, it's more than $100 billion a year positive contributor to the world economy and to humanity. And this is the biggest reason for it. What happens when you put more plant food in the air? Plants grow. So this is a 30-author NASA paper that studied from satellite data what has happened. Time period here is 1982 to 2015. And there's a scale of what's the change, and the technical thing is the plant leaf area index. How much more biologic matter is there on the Earth? And the places that are red are where that over this time period the biologic matter has shrunk, and places where it's green, it's grown. So there's more green than red. It's like 14% more plant productivity every year today because of more plant food in the atmosphere. Energy poverty, we still have 1 billion people without electricity, another 1 billion with only intermittent access to electricity. As I said earlier, 2 to 3 billion people, to me this is a shame, 2 to 3 billion people still cook with wood and dung. That's what kills 3 million people a year. Shale revolution has driven down the price of oil and natural gas liquids. Liquid petroleum gas is when people leave wood and dung, they burn LPG. It is growing in the world now. It is a massive lifesaver. And surging US production, making it cheaper, means it's happening faster. 130,000 people every day rise out of extreme poverty. That's the current rate. A lot to be proud of. So there's a lot good going on in the world. I just don't want things getting in the way of that. 14% of Americans have received a disconnection notice for utilities. 11% of Americans report keeping their homes at unsafe temperatures. California, where I lived for a long time, they're the biggest investor in an energy transition in the United States. They haven't quite got to Germany yet. They only have 60 to 70% higher electricity than the US average. But the US Census Bureau publishes the poverty rate. Everyone reads that. Is $24,000 living in rural Texas the same as $24,000 living in San Francisco? Annual income? No, of course they're completely different. So the US Census Bureau publishes the relevant data that no one ever talks about, which is the adjusted poverty rate. Income versus cost of living. California didn't crawl past, but screamed past Mississippi for the highest adjusted poverty rate in the nation. And like Germany, they get a larger percent of the total energy in California from fossil fuels than the United States as a whole, and the world as a whole. My own state of Colorado, 25% of low-income residents in our poorest region heat their homes with wood. This isn't quaint or cute, this is dangerous. I talked about the UK. Haiti and Dominican Republic border. What happens when you get fossil fuels and abundant access of modern energy? You can let the forest grow back. Haiti's on the left. Dominant source of energy, oil and gas. But they still have a meaningful percent of their population that get energy the way our ancestors did, and they deforested the country. Dominican Republic gets 90+% of their energy from fossil fuels, and you can have a rainforest. England was completely deforested at the start of the Industrial Revolution. Trees are not a giant source of energy, and they have a large economic impact. I'll end with speak honestly in this. This is an important debate. It's a dialogue we need to have, but CO2 is not a pollutant. It's an issue. We should discuss it, but we should never call it a pollutant. It's something that's going to harm human health. Without oxygen, water, and CO2, life on Earth is impossible. This is if instead of, I mentioned, the industrial activity in hydrocarbons have raised atmospheric concentration of CO2 by 50%, right? That's what's happened over the last 75 years. What if we'd shrunk it by 50% instead? Went down by 50% instead of up by 50%. That would be a crisis, because we'd be at 140 parts per million. You need 150 parts per million for photosynthesis. We would truly have an absolute crisis. And of course, we're humans, we're engineering, we would do everything possible, but we've been on a significant downward trend for 100 million years on this planet of shrinking CO2 concentration. Now, naturally, it would have taken a few more million years for this crisis. So it's not like it was around the corner, but CO2 is an essential gas. We can debate what's the right amount and all that, but it is not a pollutant. Do you believe in climate change? People say, well, Chris, but when you're going to talk, you still believe in climate change. It's not a question of faith, right? There's real data, there's a real issue, as most all issues, but it's about evaluating empirical data and trade-offs. People say, well, the science says, we're going to follow the science and do this. Science does not give policy prescriptions. Science is a tool for proving and disproving theories, and it's never settled. It's crazy. When I probably give 30 talks on climate change, 10 times they've asked people to get up and debate me instead of just to talk. The other side rarely ever will debate. That's crazy. If we're going to remake society and impact people's lives, let's discuss it. Let's debate it. Challenge these ideas. Challenge those ideas. That's what science and civil society is about. The thing I think is also very dispiriting for kids is sort of the bully, attitude of this. You can't talk about it. You're a heretic. There are no zero greenhouse gas emission technologies. Territorial greenhouse gas. Colorado is going to say they're going to go to X. United Kingdom has dropped their greenhouse gas. They're the largest percent decliner of greenhouse gas emissions. But what happened? everything that took a lot of energy to produce just left the United Kingdom. They still consume all those products. They're just made in Africa or China now, and they bring them back in. Those emissions magically go away. So when you try to do it in one town or one area, you just export your industries. You actually increase your greenhouse gases because the rich places make things cleaner and better and more efficiently than poor countries. So there's probably a net increaser of them. And just as bad, worse, is who works in energy-intensive jobs? Low-income, blue-collar people. It is brutal to live in the Midlands of England where the Industrial Revolution began. This is where modern society launched because they had cheap energy and entrepreneurial spirit and secure property rights. They've killed all three of those. Today in Liverpool, the port city of the Industrial Revolution, 1 in 3 households do not have a single employed person living there. Like, London is great if you're a banker or whatever, but when you make energy expensive, you don't hurt us, you hurt people. I'll end with a paper I highly recommend reading. Michael Schellenberg is a super thoughtful guy. He's a career environmentalist. He has a different view on climate change than me, and we've gone back and forth on it. He's, I would say, much more aligned with the Intergovernmental Panel on Climate Change. This positive feedback could be coming and all this stuff. But he wrote a piece, it's in Forbes like a week or two ago, called Why Apocalyptic Claims About Climate Change Are Wrong. And he, and as many people that I would say are sort of in the mainstream movement, they're outraged by this crazy stuff. The world's gonna end in 2030 and the species is at risk. And I mean, all these crazy claims, those claims have nothing based in the Intergovernmental Panel on Climate Change reports or any of the thoughtful scientists that fully believe in positive feedback. The worst things are coming. They have a much more serious worry about the issue than I do, but they're outraged that their movement's getting completely discredited and completely derailed. And Michael's a thoughtful guy. I'm a big fan of his. Again, although our perspectives are different, he's a thoughtful guy. But I highly recommend that piece. And I'll end there. This is a giant global issue. It's, I don't say quote unquote real. Yes, these are gases absorb infrared radiation. Yes, we're increasing them. Yes, it's going to have impacts. But thoughtful, sober dialogue, I think, is super important. Engage. The argument that, they say we're bad and we say, well, we're not quite that bad. That's not the right argument in my mind. What's the total environmental and human impact of fossil fuels is just massively positive. I spent a long time in poor countries. I've been to 55 countries. It's sort of my quest to understand poverty. I was in Tanzania a few months ago. The majority of their population still lives in huts or tin shacks and cooks indoor with wood and dung. They don't have clean lights. Their kids are burning smoke. The women are burning smoke. Their life expectancy is lower. Their quality of life's lower. What's like the highest dream for those people is the guy next door who's a little bit richer, who's got a liquid petroleum gas stove, clean air, maybe ultimately electricity with a clean light. Like the biggest challenge for the world's environment and the world's human by far and away is lack of access to clean fossil fuels, not too much fossil fuels. Is there an issue with greenhouse gas? Of course, but let's look at that in perspective with the other challenges in the world. I think the world, or sort of mainstream view, is just getting way off track here. And it's to the detriment to tens of millions, in fact, billions of people. Thank you for all your patience. And the slides, you can get the slides from our host from Capital One. There's like 40 more I didn't go through, but you have them for the data. So anybody who wants a slide, reach out to whoever contact is at Capital One. I'll be hanging around, come up and talk or whatever. So I was a little bit long, but I think it's important that we get a better understanding of this topic. Thank you.